In this video, I'll walk you through 6 AI terms you absolutely must know. The fifth one, MCP, is my favorite. Let's talk about Agentic AI first. Agentic AI is one of the most exciting steps forward in artificial intelligence. Unlike traditional AI that simply reacts to your prompts, Agentic AI can think, decide, and act on its own. Agentic AI refers to systems that can perceive the environment, reason about what actions to take, and then act. They observe the results and adjust their behavior in a continuous loop. In other words, it is AI that doesn't just respond. It plans, executes, and learns. A normal chatbot waits for a human command. It reacts. An agentic AI, however, is goal-driven. Give it a target and it can figure out the steps, take initiative, and adapt when conditions change, all without constant supervision. Imagine an AI assistant that can plan an entire business trip, book tickets, reserve hotels, and update your calendar all automatically. Or think of a system that tracks company metrics in real time, detects performance drops, and suggests or even perform fixes on its own. So to put it simply, Agentic AI is AI that acts with purpose. It doesn't just answer questions, it sets goals, takes actions, and continuously learns from experience. So next, we are going to discuss large reasoning models, or LRMs. LRMs are the next evolution of AI. They are not just built to generate fluent text like traditional language models. They are designed to reason, plan, and think logically through complex problems. Think of them as LLMs with structured reasoning. While a standard language model can give you quick answers, an LRM can actually break problems into smaller steps, plan what to do next, and even use tools to get the right results. For example, a regular AI might simply answer like the capital of France is Paris. But an LRM can handle logic like if A implies B and B implies C, then A implies C. So the transitive relations LRMs can easily handle. In short, LRMs don't just generate words. They think through problems the way humans do. So this is how LRMs work. First, the model begins by understanding the input, whether it is a math problem, a logic problem, or a planning task. Then it breaks down the question to truly grasp what is being asked. Next, it decomposes the problem into smaller, manageable tasks. Here's where chain of thought reasoning comes in. The model thinks step by step, working through logic, facts, or calculations instead of jumping straight on the answer. Sometimes when precision is the key, the model can call in external tools like calculator, an API, or a database to check numbers or fetch data or confirm details before continuing to further steps. Finally, it brings everything together, crafting a clear, coherent answer. Then it double-checks its reasoning, reflects on possible errors, and refines the final response before presenting the result. So this is how LRMs works through its reasoning. Third, we are going to discuss vector databases. Vector databases are a special kind of database designed for the world of AI. Instead of storing traditional text or numbers, they store something called embeddings. Embeddings are numerical vector representations of unstructured data like text, images, or audio. These embeddings capture the meaning of data. That means instead of searching by exact keywords, you can search by similarity of meaning, which is also known as semantic similarity. So the database can find things that feel related even if the exact words don't match. So here is how it works. First, your data, let's say documents or image captions, is converted into vectors using an embedding model. Then those vectors are stored in the vector databases. When a user sends a query, the query is also turned into a vector, and the database searches for items whose vectors are closest. They use mathematical measures like cosine similarity or Euclidean distance. Then the closest matches are returned as the most relevant results. Vector databases power many of today's AI applications, from semantic research and recommendation systems to the retrieval step in RAG pipelines, and even in anomaly detection systems that spot unusual patterns in data. In short, vector databases let AI understand and connect meaning rather than just match words. Fourth, we are going to discuss Retrieval-Augmented Generation, which is RAG. Retrieval-Augmented Generation is an AI framework that combines two steps. One is retrieval, that is searching external knowledge base, and second is generation, that is producing natural language answers. So instead of relying only on what the model learned during training, RAG allows it to fetch up-to-date or domain-specific information from external sources like vector databases or stored documents, leading to more accurate, factual, and grounded responses. This is how RAG works. User asks question. For example, explain the new European AI Act. The system then converts the query into embedding vector and searches an external knowledge base, for example, PDFs, websites, or enterprise data, for relevant documents using semantic similarity. Next, the retrieved informations are added to model's context. Next, the language model, for example, GPT or Claude, uses the augmented context to generate a coherent, fact-based response. RAG matters because it reduces hallucinations, which is wrong or made-up information sometimes AI gives. It keeps AI up to date without retraining. And it enables domain-specific knowledge, for example, company documents or company laws or new medicines. So, RAG gives up-to-date context to AI models, which in turn produces answers which are more accurate and precise with respect to the query you have asked. Now, let's talk about something called the Model Context Protocol, or MCP. Think of MCP as the universal connector for AI systems. It is a standard way for AI models, agents, and assistants to safely and consistently connect to tools, data, and external systems. It was introduced by Anthropic in 2024 as an open standard that gives AI a structured way to access the outside world. It is kind of like a common language for AI integrations. You can think of MCP like a USB-C port for AI. Just like every modern device uses one simple port to connect to chargers and accessories, MCP gives AI a standard way to plug into different tools and data sources. Without MCP, every AI app would need custom connections, one for each service or database, leading to a messy integrations. MCP simplifies that. Instead of many-to-many, it becomes one-to-one connection. Build once and connect everywhere. So this is how MCP works. There are three building blocks. First is tools. These are actions the AI can perform like search web or send email. Second is resources. These are data sources such as documents, files, or APIs. And third is prompt templates. These are reusable instruction sets or workflows that guide the AI's reasoning. And with the help of these three building blocks, MCP reduces the need for custom engineering, and developers can define what data or tools the AI can access. It also enables dynamic context. The AI can fetch live, up-to-date information instead of relying only on what it was trained on. MCP is a big step toward interoperable AI. That means once a tool or data source supports MCP, any AI that understands MCP can use it instantly. Here's a quick look at how MCP actually works. The AI application or agent acts as the MCP client. It connects through the MCP connector layer, which follows the standard protocol. Various MCP servers like databases, APIs, or tools declare what they can do. The AI discovers those capabilities and picks the right tool or resource. Then it sends a structured request. For example, add a new task or fetch project data. The server executes the actions and returns the results. The AI integrates that information into its reasoning and delivers the final response. In short, the Model Context Protocol gives AI a universal, secure, and structured way to interact with the real world, making agents more capable, reliable, and connected than ever before. Next comes MOE. Let's talk about the mixture of experts, or MOE. MOE is one of the most powerful ideas behind today's large AI models. In simple terms, it is a way to make huge neural networks smarter, faster, and more efficient by splitting the work across specialized mini models called experts. Instead of one giant model trying to handle everything, MOE divides the model into multiple experts, each trained to specialize in certain topics or skills, like language, math, or reasoning. Then there is a gating network, a smaller controller that decides which experts to activate for each input. So when a question or image comes in, only a few relevant experts, let's say 2 out of 64, are used to process it. This makes computation faster, cheaper, and more focused, while still keeping the model's full knowledge available when needed. The model receives an input. It could be a sentence, an image, or a query. The gating network analyzes that input and picks the most relevant experts. For example, a science question goes to the science expert, while a math problem goes to a math expert. Those selected experts work in parallel, each processing the data in their own way. Their results are then combined, often using a weighted average to create a single refined output. You can think of MOE like a hospital system. Each doctor is an expert, one in cardiology, another in neurology, and so on. When a patient arrives, the receptionist or the gating network listens to their symptoms and sends them to the right specialist, which makes the whole process efficient, accurate, and scalable. So those were the 7 terms which I think every AI enthusiast should know, and I hope I was helpful. Please like my video and subscribe my channel.